there were problems with it. So I'm starting the live stream on YouTube.
So you will tell me when to start with. Joining, or is it stabilized more or less?
I think it's locally stabilized. So let me introduce your talk. So I just need the right title.
Yes.
Just a second. Let me look for the right title. So of course. Yes. So I guess Avraham Aizenbud from our institute doesn't need any introduction on this seminar, so I'll announce the title, Bounds on Multiplicities of Symmetric Pairs of Profinite Groups.
So thank you very much. I'm sorry for the wrong title here. It's a related talk, but it's not the same talk, sorry. So this is a talk about joint work with Nir Avni. So let me start with some basic conjecture. So we have a reducible algebraic group scheme acting on a spherical scheme. So what do I mean by this? I mean that over any algebraically closed field, so it's all so G is a group scheme, so group scheme over Z, and X is also over Z. So, but when you take any algebraically closed field, you base change to this field. Then you get an algebraic group acting on an algebraic variety, and you want this action to be spherical, meaning that the Borel subgroup of G acts with finitely many orbits of X. So I have such a situation. And now we're interested in those multiplicities. So consider this most inner thing in the parentheses, the dimension of the multiplicity space of rho inside functions on X of F. But who is F? So F can be varied. And so also rho. So we want that when we range over all local fields or finite fields, and then range over all irreducible representations of G of F. I'm sorry, I will close the window so it will be quieter. So we are ranging over all local field or all finite field, and then we range over all irreducible representations of G of F. And we want the multiplicity to be not only finite each time, but also uniformly bound. Of course, one has to explain what does C infinity mean and what kind of irreducible representations we're doing. So we basically do the standard thing. If the field is finite, so nothing to explain. The smooth functions are just functions and representations are just representations. But if the field is local, then in the non-Archimedean case, smooth means locally constant. And in the Archimedean case, like R or C, smooth means actually smooth. Okay, so you can study this conjecture on different levels. You can start from the inside just to prove this is finite. It's also sometimes not trivial and not known. You can fix the field and then try to prove this uniform bound, but this fixed field. And you can try to go all in and prove for when you vary the field. So what is known or what was known? So there are lots of things known when you don't range over the field. So basically, if you fix the field and the field happens to be Archimedean, then Kobayashi and Oshima, and then Kurtz and Schlichtul gave bounds, explicit bounds that not only show that this dimension is finite, but also it's uniformly bounded when you range over reducible representation. If it's non-Archimedean, then for symmetric spaces, it was shown by the norm that as the multiplicities are finite, and for spherical spaces, not all of them, but many of them, it was shown by Skaradis and Vertesh. Sorry about that. That the multiplicities are finite. But in this case, in general, or even except for some cases, it's nothing F uniform is known. So nothing even uniform overall. In the non-Archimedean case, even you don't have results uniform overall. When you do have uniform results, when the multiplicity is 1. So if this multiplicity is 1, so we can say that X is a multiplicity-free space, or we can say that if X is transitive variety, so X is G modulo H, so we can say that G and H are Gelfand pair. So if the pair is Gelfand, then in many cases it's proven that the pair is Gelfand, and in this way you can not only prove that the multiplicities are finite, you can bound them by 1. One remark that I didn't say, I wrote here X is just a G scheme, but this question becomes more interesting when G acts transitively on X. Because if it's a finitely many orbits and you're interested in bound, so usually you can bound it orbit by orbit. So in the Archimedean case, it's not that simple, but overall, it makes sense to start to study one orbit. And if there are infinitely many orbits, then there is no chance for some multiplicities to be finite. So case closed. Anyhow, it's not spherical if there are infinitely many orbits. If the multiplicity 1, you can prove it, but also sometimes if it's not 1, but it's close to be 1, it's related to some other situation when it's 1, then you can prove it. So probably the first results on multiplicity or Gelfand pairs in this non-compact setting are by Gelfand and Kashdan, and then in the real case by Shalaika, and then there was plenty of results about Gelfand pairs. And there are some examples that are related to Gelfand pairs. For example, if you have something with GL, which is Gelfand pair, and then you pass to SL, so maybe the multiplicities are not 1 anymore, but it's very easy to show that they are bounded. And there are also an interesting class of examples, when the pair are not Gelfand pair, but they are cuspidal Gelfand pair. So if you're working for non-Archimedean case, you study cuspidal representations. And for cuspidal representations, sometimes the multiplicity is 1, although in general it's not 1. And there are many people that are doing it. I think the most dominant name in this area is Hakim. And once you have cuspidal multiplicity 1, it's rather easy to deduce that you have bounds in general on multiplicities. But many pairs are not Gelfand pairs and not related to Gelfand pairs and not cuspidal Gelfand pairs. So I think that in general, this direction cannot give the full conjecture. So for full conjecture, you will need some different techniques that are not related to Gelfandness for multiplicity 1. And recently, or maybe not that recently anymore, almost 5 years ago, we and Shai Schefter, we proved that for finite field case, the multiplicities are bounded. So we did it for type A, and Shai Schefter did it for the general case. And of course, in finite field case, the inner parentheses are very boring. So of course, the multiplicities are finite because the dimension of irreducible representations are finite. And of course, the maximum over all irreducible representation is finite because there are finitely many irreducible representations of a finite group. But there are infinitely many finite fields, so the general question still makes sense. And okay, we'll discuss at some levels this result. Okay, so what is some long-term strategy for the general conjecture? Oh, it's not the strategy, it's a strategy. Strategy that I hope that can give something. Yeah, so we said that the real case is basically done. So we care about the non-Archimedean case, and before the non-Archimedean case, we can start with the finite case, which is already done. And here the main method is to use geometrization of representations. So instead of study, say, characters of representations, which are functions, we study Lustig character sheaves, which are sheaves with give it geometrization of those characters. And so once you understand them, you can bound the multiplicities. The next stage is to pass to finite rings like ZP. And there you have such an exact sequence. So you have, say, GLN ZP. Of course, you can do it with other groups too. It has this finite quotient. And the kernel is a first congruent subgroup. It's a kind of complicated group, but it is a poor P group. So it's not that far from being commutative. So to prove some bounds on multiplicity here, it's much easier. And here we know from the previous step, and then we can hope to get to the thing in the middle. So here I want to comment that a priori there is no reason to expect the conjecture to be true for ZP. So somehow for QP it looks very natural. It's correct for principal series representations. We have some intuition. But for ZP, the representation theory, it's much more wild. And in general, we don't expect it to behave as nicely as periodic representation. So this kind of risky part of the strategy, it might fail here. But let's assume it works. And then the next stage is to go to the periodic case, but not all representation, but only cuspidal. And the reason why cuspidals are easier, that at least in some generality, any reducible cuspidal representation is an induction of a representation, a reducible representation of G of Z. Again, not all. Usually, if you just take representation of G of ZP and take its induction, you get something very reducible, yes. But for some small subset of representation of G of ZP, the induction going to be reducible, and then they're going to be cuspidal representations of the group G of QP. Okay. So this give a hope to prove the conjecture for cuspidal representations. And from cuspidal to general representations, it's rather easy because any reducible representation is a subquotient of this induction. So this part is rather easy. So let's see what is known. So as I said, first step one is known, it's basically completely done. And step two is what I'm going to tell today. Surprisingly, it works, not in general, with some limitations. I would say what are the limitations, but we have bounds on the multiplicities. Step three is probably the hardest step at all from the all. I still have hopes about it, but it's going to be hard. And step four is easy. Okay, so let me start with step one, the step that is actually done. So here is a theorem. We have a reductive group scheme and X is spherical G scheme as before. And now we take maximum over all finite fields, maximum over all irreducible representations, and then compute these dimensions. So here we don't need to discuss smooth functions, just set theoretical functions like this. And this multiplicity is finite. So here is some sketch of the proof. So we use Lustig character sheaves and we geometrize all the situation. Yeah, I didn't say. Yes, so maybe one motivation for the conjecture is that for principal series representation, it's rather easy to prove, at least in the non-Archimedean case, it's rather easy to prove. In the Archimedean case, it's also true, but a little bit more tricky. And once, so the computation in the principal series case is you just it's parabolic induction from the Borel. So you use the fact that there are finitely many orbits and bound to multiplicities. So the Lucy character shifts, they are also, in a sense, more or less all of them can be considered as kind of principal series. They're also induced from a torus, but not via Borel, but the torus is non-split torus, but there's some geometric construction of induction. So you can basically use the same argument, but you do it in the language of character shift. So at the end, instead of multiplicities, which are a number, you get a vector space that models a multiplicity, or in fact, complex of vector spaces. And these complex of vector spaces end out with automorphism, which is coming from Frobenius. And the trace of this automorphism going to be the multiplicity or up to some factor of the multiplicity. So now you need to bound this. And as usual with character shifts, it's rather easy to see what's going on when you fix P and see what happens with larger extensions of FP. And the asymptotic, when n is very large, is controlled by the highest homology, because you consider trace of Frobenius. So trace of, and when you take powers of P, so Frobenius becomes powers of the same operator, some basic FP Frobenius, and sum of powers of eigenvalues. So of course, main contributions comes for the maximal eigenvalues, and they determine what's going on when n is very large. So you not only can bound the multiplicities, you can very explicitly bound them, and when the Frobenius is when the power is very large. But then you want to go back, to extrapolate back. And so to get some bound is probably rather easy, but we wanted some very explicit bound, the same bound that we get for large n, we want also to be correct for small n. And here you use some this dual information. So for one hand, the multiplicity have this nice formula of sum of powers of eigenvalues, because they're trace of certain operator. And for the other hand, multiplicities are natural numbers. So if you have a sequence of natural numbers, which are all described by some nice formula, and it's bounded sequence, it's very easy to show that it's in fact periodic sequence. So it's not only bounded, it's bounded by its limit, the infinite, by its lim sup. And in this case, where you can get bound, which is much more uniform and much more explicit. Okay, so let's go to the goal of today. Now, maybe any questions until now? No questions. Okay, so let's recall what are symmetric pairs. So I'm not sure how well symmetric pairs behave in characteristic 2. So let's assume that characteristic is not 2. And we have a group. So it can be a finite group, but it can be also a algebraic group. And then I want the characteristic of the base field to be not 2. I have involution of this group. And G theta is a fixed point of the involution. So the pair G comma G theta is symmetric pair, and this quotient is a symmetric space. And a classical result, I don't know how to attribute it, but it's known for a long time that all symmetric spaces are of reductive groups are also spherical spaces. And the prototypical example of symmetric pair is we take the group H times H, and inside it, we take the diagonal. It's of course a fixed point of the standard involution of the flip. And the quotient going to be H, and the action will be just a two-sided action. So this is a symmetric pair, a symmetric space. And it's also, of course, a spherical space. So it's a prototypical example for both of them. And in a sense, when you study this relative representation theory of this space, so you take functions on H and decompose it with respect to H times H, you see all the representation theory of H encoded inside it. You all know this Maschke theorem or whatever. So at least in many many cases, many kind of generality. To study this space is more or less equivalent to study irreducible representations of it. And in this case, of course, the multiplicities are very simple. They are either 0 or 1. And you can say exactly when they are 0 and when they are 1. And you can consider the statement as some manifestation of Schur's lemma. So study multiplicity in general is kind of extension of this basic observation. Okay, so now let us formulate the main result. You have a reductive algebraic group, and X is a symmetric space. Everything is over Z for now. And now we have this kind of uniform bounds. We range over all primes, M larger than 2. And then we take ZP and take a reducible representation of ZP. Now we consider this regular representation of functions on ZP. So we can consider smooth functions, but we can also consider continuous functions to give the same answer. And you consider the multiplicities for rho inside this. Yeah, you can also consider L2 function. It doesn't matter because this is a compact group. And X of CP is a compact topological space. Okay, so you see here basically 2 drawbacks, and we talk only about symmetric pairs, and we talk only about ZP. So before we wanted something for arbitrary local field, so we can consider the ring of integer of a local field. But here, of course, it will be true for some fix, if we fix some degree of extension, but we can't get a uniform result when you run over all extension of a given local field. What you can get, or what we did provide, is a uniform result when you get over or run over all purely unramified extension of a given field. But when you go to, sorry, purely ramified extension of a given field. But when you go to unramified extensions, control on the multiplicity gets lost. Yeah, and another remark which you don't see from the formulation is that those bound, we have some explicit bound, but it's very, very large. We didn't write it down explicitly, but it's a very explicit algorithm, but it gives something like more than tetration. Yes, it's not only the super exponential, it's more than tetration. It's something around the Ackermann function, maybe a little bit smaller.
Do you think it's true actually in a more general situation for local ring?
Yes, I think.
So from the cube, I don't know, from local field, you can actually go back and say that it must be also.
No, this I can't say because the vast majority of representations of G of ZP does not relate to any representation of G of QP. There are much more of them in a sense. Of course, there are only countably many of them, and there are uncountably many. But if you consider cuspidal representation, say that there are much more representation of G of ZPs and cuspidal representation of G of QP. So there is no good reason to expect it. But okay, but this theorem is already, I think, some kind of motivation.
And I'm sorry, maybe I was supposed to ask it before. What is the constant in a finite field? Do you get it in terms of the classification of representation and I don't know, some parameters for X? What is that number?
The constant is more or less what you would expect. So what you expect for principal series representation is just a number of Borel orbits on the spherical space, which is finite, so it gives you the finite number. So here,
okay, so you do
this number, because this number is a bit tricky, so you can work over algebraic closure, and then algebraic closure you have finitely many orbits, but each orbit can give you a number of different fields. So you basically get the worst case scenario. So you take the number of orbits with over algebraic closure, and each of them you take with some weight, which is some finite number of how bad can it be, how much can it in the worst case scenario, split over the finite field. And also all of this, you have to multiply by some small, relatively small number that you have in this Lustig theory, because difference between Lustig character shifts. So the difference between characters and quasi-characters, or almost characters, sorry, each of them is combined, like there are small, relatively small matrices that translate between them, so the size of those matrices. So this is relatively small, but of course, if your group is GL 3 to the power 100, it will be, I don't know, 3 to the power 100, so it's not necessarily small. Okay, so our proof is by induction, and as usual, when you prove something by induction, you often find that you have to prove something stronger. So we did prove something stronger, and here is a stronger statement. So we range again over all primes, but this time we range over all finite groups. But we need somehow to bound their size. So here's the way we bound their size. We want that there will be a map phi from the finite group to GLN FP. So P is this P. And we don't demand the map to be embedding, but we want that the kernel of the map will be a P group. It can be very large, but a P group. And then we range over all involution of gammas and of gamma and all irreducible representation. And then we have a bound on the multiplicity. So this time I wrote the multiplicity after Frobenius reciprocity. So instead, home like this, just invariance with respect to gamma to the power 2. So it's rather easy to deduce from this second theorem and this first theorem.
I'm sorry, you also take supremum over all case. So the only condition is that the kernel, the size of the kernel is a prime power.
But not just a prime, the same P where this P and this P are the same. It can be arbitrary, but
I see.
So like it's not like a good example is G of ZP. G of ZP is infinite group, but you can quotient it by some very, very deep congruent subgroup. And then you can embed it into G, or you can map it to G of FP, and the kernel will be a P group. So this is example, and this is the thing. Yeah. So okay, this is also only finite groups, but and here we're kind of discussing profinite group. But what are profinite group? A representation of profinite group, any specific representation is a representation of its finite quotient. So if we have some uniform result, so you get in fact one result for profinite group.
Why we are considering this theorem, this situation? So what is going on?
Why we do the second theorem?
Yeah, so you somehow need to care for weird subgroup of GLN.
Yeah, exactly. You can ask why would we care? We have nice algebraic groups which we like, and we go to this a wild place when you can find general groups. And maybe there was a way around this, but somehow this is the easiest way we found. But this is what happens when you work by induction. So we start with nice groups, but then we study it by induction. You will see in the argument, I will talk about the argument. At some point, you see some other groups, which maybe not general finite groups, but it's very hard to say what exactly they satisfy. So we say, okay, let's prove for general finite groups, and then our induction is just work as easy. So yes, we prove this theorem not because we wanted to, but because we had to. But of course, it implies a previous one. And in fact, it implies even more general theorem. So let's squeeze this more lemon to its end. You can range over all prime numbers, all local fields, but here you limit something. So you want them to be purely ramified extensions of those base fields. One of them, never mind who, but only purely ramified extension. Of course, you can allow also some unramified extension, but you then will have to bound the unramified. You range over all algebraic groups, connected algebraic groups. Oops, I should have wrote here connected, of dimension n. And over all compact subgroup of G of F. So it can be G, but you can run over all compact subgroup. And now you can range over all involutions of K and all your this representation of K, and you bound and the multiplicity. Very uniform. The only thing you have to bound is this dimension of G. And the unramified part of the extension. Okay, any questions about the formulation? No.
So again, here you also find an explicit bound, or is it an existential?
It's explicit but very ugly. It's very, very large.
So you don't expect it to be optimal in any sense?
No. Okay, first of all, let's go a bit back. For example, this conjecture, this theorem, I expect to hold even when you range over, say, unramified extensions of F. This, okay, it's even not clear what does it mean, but it is clear. You can write here FQ instead of FP. I don't expect it to be correct when you go over general finite groups. And this also, if you allow unramified extension, I don't expect it to be bounded. If you allow any compact subgroups, if you allow, say, open compact subgroup, there's a different story. But if you run for arbitrary compact subgroup, it's probably too general. And also here I maybe don't know. Here I don't have enough. And about the optimality, so for the reasonable theorems, so for this theorem, and for reasonable special case of this theorem, then certainly the bound is extremely far from being optimal. For the general case, it's of course not optimal because we didn't optimize it, but maybe the optimal bound is also very, very bad. But the general case is probably not the conceptual interesting one.
How those bounds expect to look like?
The actual real bound, I believe that there is some exponential bound, which is similar to the number of Borel orbits. Yes, Borel orbit, open Borel orbits. Asymptotically, it's all more or less the same. It's something exponential, maybe slightly super exponential, like for factorial. So I believe that this is a. If you just want to know the range, if you want concrete numbers, then it's very hard. Yes, for example, we have some conjecture when a pair is a Gelfand pair, but it's hard. But the range is probably around something exponential, maybe slightly over this. Okay. So can I continue? Okay, so I know that in talks you usually should not get into proofs, but this is a Zoom talk, so you can probably all put yourself on mute and switch off the camera, and nobody will know. So I will try to give some less boring ideas from the proof. I hope it's still interesting. So we prove by induction, so we need some invariant of this finite group. So the theorem that we prove is this theorem with a finite group. So we need some invariant of the finite group on which we are going to do induction. So this is the invariant. We take our finite group and we ask what is the minimal dimension of a connected reductive algebraic group G, such that gamma can be embedded into G. And we denote this number by RDP of G. So gamma can be embedded into G of FP. Yeah, so this invariant depends on P, but the bounds will not depend.
Excuse me, what is gamma?
Gamma is a finite group.
Thanks.
Just general finite group, and this invariant kind of behaves like a dimension. Okay, but since we're interested in things that are not sensitive to P subgroups, so we also define the reduced reductive dimension of gamma. So let's call it reductive dimension, and this reduced reductive dimension. So we quotient out by the P radical. The P radical is a maximal normal P subgroup, equivalently just the intersection of all P0 subgroup. We quotient out by this, and then we compute the reductive dimension, and this we call the reduced reductive dimension. So the theorem, let me go a bit up. So this theorem can be reformulated now in the following way. You range over all gammas of given reduced reductive dimension, and then you want to bound the multiplicity. And of course, in a way that will not depend on P. So you range over all P's and all gammas of given reduced reductive dimension with respect to this. Okay, is it clear? Okay, so the main part of the proof is cheating. And so this is a very beautiful theorem by Larsen and Pink, which basically says that all these steps that we went to this wild world of finite groups is not really make the life harder. So, so the Larsen-Pink theorem, it's not the exact formulation, but essentially what does it mean? That if you take a finite subgroup of GLN of FP, and in fact with Larsen-Pink it was with FP bar, but we care only about FP. It's make it much simpler, but this is the part that you actually need. And when we take finite group of GLN of FP, then it's essentially an algebraic subgroup. So what do I mean by this? So of course it's algebraic subgroup because it's a finite group, so every finite group is algebraic subgroup. But if you try to write large finite group as algebraic subgroup, you see it's very, just without thinking, it will be very disconnected group, and we will have to use lots of equations of very high degrees. So you want to bound the number of equations, or let's say the degree of the equation. So the complexity of the group, it's bound the degree of equations that defines it. And then in particular, you also bound the number of connected components, so you cannot just make it as a finite groups, which is difficult. Algebraic group, which is distinct. And the theorem is that you actually can do it. There are some caveats. So for example, if the main problem is with tori. So if you take GL1 and you take subgroups of GL1s of FP, so GL1 of FP is just a cyclic group, and they can be basically as wild as you can imagine, because depending on the P minus 1 can have many different prime factors, and you can do lots of fun. But basically the Larsen-Pink theorem say you that this is it. Okay, so I will not give explicit formulation of the Larsen-Pink theorem, but I will say the two corollaries that we use for it. So the first corollary is about our invariant, Rp of gamma or Rp of delta. So I want this invariant to behave like a dimension. And because of Larsen-Pink theorem, I more or less can ensure it. So what do I mean by this? So I want some monotonicity. So if we have group gamma and subgroup delta, we want some inequality like this, that the reduced dimension of gamma is smaller than the reduced dimension of delta is smaller or smaller or equal to the reduced dimension of gamma. So the reason why I cannot ensure it, that sometimes the radical of delta can be larger than the radical of gamma, will not be included in the radical of gamma, because delta became smaller, but maybe new elements became part of this P radical. And in this case, when you quotient out by the radical, delta stops to be a subgroup of the gamma, and we get delta is subquotient of gamma. And in general, subquotient, it's not clear that you can embed the same places when you can embed gamma. But the statement is that in this case, you can find a subgroup of delta, such as for this subgroup, the reductive dimension will be smaller. In fact, strictly for smaller because the radical, you actually added something to the radical, so you quotient by something more and something significantly more. So this is a P group. So if it's larger, so it's at least P times larger. So you expect the dimension to fall down at least by 1. And now you want to control on this index. So of course, you can take delta 0 to be trivial, but you don't want it to be trivial. You want it to be rather large in delta, so that the index will be controlled by this invariant. What do I mean by controlled? I mean that for any value of this invariant, there is some value that controls the index. So it doesn't have to be linear, doesn't have to be quadratic. It can be completely insane, but once it's fixed and explicit in our case, we're happy. So this kind of monotonicity of reductivity dimension, reduced reductivity dimension. And the second corollary is what happens if we don't have radical, don't have p-radical. So in this case, the statement is that we can go to some smaller subgroup, gamma 0 inside gamma. And again, we'll have control on the index. And gamma 0 is essentially G of Fp for some reductive connected algebraic group G. And what do I mean by essentially? In this case, it's very clear, essentially meaning that it's between this group and the derived group of the Fp points. So here exactly you see that all the taux disappears because the taux, so if G is a taux, then this statement is meaningless. It's just saying that gamma 0 is a subgroup here. And we want control both on the index of gamma 0 and the dimension of G, and the controls will be in terms of RDP of gamma. So in this case, the control and dimension of G is very explicit. So for this formulation, it's just the dim G, and in a moment it will become twice dim G, but the control on the index is very, very bad, but control. So, and we need slightly stronger statement from both of these corollaries. We need both of those corollaries to be valid in S2 equivariant situations. What does it mean? So it means, for example, in the first corollary, that if gamma have an involution, then, oh sorry, even if just delta have an involution, you don't have an involution in gamma, then you can find delta 0, which will be invariant with respect to this involution. And the second corollary, yeah, also I didn't wrote here, I want also delta 0 to be normal inside. But this is not a big deal. It becomes more problematic when you want to do both invariant and normal, but again, not a big deal. And here, if gamma have an involution, I want gamma 0 to be invariant with respect to this involution, and G also to have this involution, and the embedding, this embedding to be equivariant with respect to the involution. So entering this involution makes dimension of G to be a priori twice larger, but okay, it's okay. Once we have control, we're happy. And in fact, if you just have those two corollaries, so you can at a black box deduce S2 equivariant case. So at the end, if there will be time, I can discuss it. Any questions about this slide? Okay, no questions. Okay, other ingredients that we use in the proof.
Rami, so will you explain later how this ingredient helps?
Yes. I want kind of start with all the ingredients and then to do the Lego of how they go inside together. So other ingredients is a Clifford theory. So I just want to, can you excuse me for 5 seconds? I will take something to drink.
And this doesn't even involve quantum mechanics.
So we have, sorry, sorry, one more time. Okay. So we have a short exact sequence, say, of finite groups. So we have group G and we have its quotient H and a subgroup N. So in our case, N will be the radical. In the slide that you saw before with this GLN ZP and GLN FP. So N going to be the kernel and H going to be GLN FP. So this example you should think of. And you have an irreducible representation of G, and you want to understand it in terms of irreducible representations of H and irreducible representation of N. So Clifford theory will give you the following thing. It gives you a subgroup S, which is some subgroup in the middle, such that your representation pi is induction from irreducible representation of S. And this irreducible representation is N isotypic. So when you restrict it to N, you just direct sum of the same irreducible representation with itself many times. So in a sense, it gives you understanding of irreducible representations of G in terms of those two groups. Okay, another ingredient is a finite field case, which we already discussed. So it's of course important part of this, of the general case. And in this short exact sequence, so this is going to be more or less a finite field case. And another ingredient is group of odd order. So in fact, we need it only for P groups, but P is odd, so we can do it more generally for groups of odd orders. So in this short exact sequence, N will play the role of group of odd order. And there we need not only our result, but in fact, much stronger statements. But all the statements there are just given by very simple observations that group of odd order have a square root. So if you're teaching a basic course in group theory, so you can give it as an exercise that a group of odd order, any element have a unique square root, and this is nice to know. And the last ingredients are some homological estimates, which I will explain how they turn into the picture, but I want first to introduce them. And so we have finite group gamma, and we have involution of it as to acting on it. So we can compute the first homology, and the statement is that it's bounded by something which will depend only on this invariant RDP of gamma. And then we need also bound on a second cohomology, but completely different second cohomology. We start with the finite group gamma and act on this group of roots of unity of order, which is power of P. And here we not only want to bound it, we just want to prove that this homology is trivial whenever P is large enough, but large with respect to this number, R, P bar of gamma. Okay, so now let me describe the flow of the argument. So the first part of the argument are special cases. So we start with the special case of group with odd order. So we have the square root, and here what we can prove now. First of all, we can prove that this first homology is 1. You don't need any bound, it's just exactly 1. And you can prove the Gelfand criterion. So we want to prove multiplicity 1 for the pair gamma, gamma theta. So in fact, we want to bound the multiplicity, but in fact, we have much more in this case. If the group is of odd order, so any symmetric pair is multiplicity 1. And not only it's 2, you have the standard proof box. So you have the Gelfand criterion. Gelfand criterion says that you should choose some anti-involution. In this case, you take this involution theta of G inverse, this anti-involution, and you take the double coset with respect to this subgroup gamma theta, and each double coset is invariant with respect to this anti-involution. Or in other words, you have such an equality. So once you have a Gelfand criterion, you have two things. You first of all have the Gelfand property, which means that the multiplicity is smaller or equal to 1, which of course means it's bounded. But you also have this property that we call the Lapide-Prasad property, because I have a conjecture that in some cases, in a sense, it has to be satisfied, but for groups of odd order, it just satisfies on the nose, because each time you have Gelfand criterion or Gelfand-Kashtan criterion, you have it more or less automatically. So I think it's by result by Jacquet and Drali, so I first saw it in some special case, but the argument is general. In their paper, I don't know whether it was known before. Or this. So such an implication that the Gelfand property implies this. I don't know whether it was known before, but it goes back at least to Jacquet and Drali. So let me explain what is written here. That so not only that the multiplicity is less than or equal to 1, if it's not 0, rho have to be, in a sense, theta anti-invariant. So when you take rho and apply theta, you get rho star. So it's also invariant with respect to this anti-involution, but this time anti-involution on representation. Okay, so this proves the conjecture for groups of odd order, of course, but it also gives lots of other information. Now we need to discuss groups with trivial p radical. So this is kind of the other extreme.
Rami, excuse me, wait a second. I cannot understand how this solves.
What?
So, am I supposed to understand now in
yes.
very general lines the case of groups of odd order?
Yes. So let me repeat what you don't understand.
No, I understood some ingredients, but I didn't get how it proves. Or,
the case of group of odd order. So first of all, you want to prove this the Gelfand criterion. So I claim that if the group is odd order, then any symmetric pair is a Gelfand pair.
And that's because the cohomology vanishes?
No. That's because the Gelfand criterion works.
And it works because we have square root? Or?
Exactly.
I see.
Yeah. This is
yeah.
Once you have square root. The same reason square root also give you vanishing of first cohomology, which will be important later.
Okay.
You have so the Gelfand criterion works, so you have the Gelfand property. So we are done for this case, but for the future we want to know more than just the conjecture and more than just Gelfand property.
I see.
You also want this Lapide-Prasad property, but you also get it because of the Gelfand criterion.
I see. Thank you.
Thank you very much. As the case, so now we go to the other extreme, the case of groups with trivial p radical. So here we use Larsen-Pink theorem, and Larsen-Pink theorem says us that if we have a group with trivial p radical, we can replace it with a group of Lie type. And for finite groups of Lie type, we can bound the multiplicities, as I described before by Shai Schechter. But in fact, we need a little bit more. We need not only to bound the multiplicities, but also to bound twisted multiplicities. So we have some character of gamma theta, we still can get bound on multiplicities. I also can say that it's uniform on all characters of gamma theta, but this is not very interesting statement because there's no too much. For finite groups of Lie types, there is no too much characters of gamma theta. And here, another point which makes it a bit disappointing. So for finite groups of Lie type, we can prove this twisted bound. It's more or less the same proof as non-twisted case, and everything is good. And this is the only thing that we need to do, we need to use in order to prove our theorem for those poor finite groups or finite groups which have large p-radical. But at this point, we cannot prove, or our argument does not give finite multiplicities for twisted finite multiplicities for poor finite groups or for groups with large p-radical. So yeah, it's not a problem because it's not a proof by induction, but it is disappointing because I do think it's correct. So maybe one can adapt the argument. We try for some time and fail. So I think it might be interesting. Yeah, we didn't try too long. At some point when the students we don't need it, so we proceed further. But I think it's still interesting. What happens? Okay, now the last special case, which is rather general already, we consider general group, but only representations which are isotypic with respect to this to the p-radical. So how you can guess that this will become relevant because of Clifford theory. So there we also can prove a statement using the two previous cases. How do we do it? So first of all, we use this vanishing of second homology. And okay, so maybe I should recall something from Clifford theory, or in general, you have a representation which is atypic when you restrict it to n. So you can hope that the multiplicity space, maybe I should write it. Just a moment. Notation. So you have a representation pi. Where you can annotate. You have a representation pi. And you know that when you restrict it to the radical, say, let's note it by n for now, it is atypic. So you have it's atypic, so it means that it's equal to some rho 1 time, which is a representation of n, times some v, which is a multiplicity space. So you can hope that your group gamma modulo n acts in v. But so you almost can get such action by the Schur lemma, but when you look at the details, you see that it's not an actual action, it's only a projected action. It's defined up to a scalar. So you can try to fix the scalar, and you see that there is some abstraction to fix the scalar. And this abstraction lies in the second homology. So of gamma, in fact, not with coefficients here, but with coefficients a priori in C star. But if you know something about the dimension of rho 1, and rho 1 is a representation of n, so its dimension, it's a p group, so its dimension going to be a power of p. So once you know it, you can replace this C star with, never mind, with this subgroup. With this subgroup of C star, so the groups of all roots of unity of co-factor. So once you know this, if the second homology vanishes, then there is no abstraction, and then this multiplicity space, have an action of gamma modulo n. So in a sense, you decompose your representation. So what you actually get, you get that your representation is tensor product of two representations, rho 1 and rho 2, where rho 1 is trivial on this radical, so it's an opposite order than I said before. And rho 2 is irreducible once restricted to the radical. So in fact, rho 2 is, we say that our representation rho is isotypic when you restrict it to the radical. So rho 2 is its type, and rho 1 is the multiplicity. And rho 1 there is no action of the radical, so you can think of it as a representation of the quotient. So now you can compute multiplicities of rho with respect to gamma theta. How you do it? You decompose rho. And now you first of all compute invariance with respect to this subgroup, theta invariance in the radical. But the radical acts trivially on rho 1, so in fact you only do invariance in rho 2. But rho 2 is irreducible as a representation of the radical. So you can use the first case, a case of group of odd order, and get that this space is one-dimensional space. But here's a small nasty surprise. This is one-dimensional space, but it doesn't mean that it's trivial space. So this space still have a non-trivial action of this group. So it's a character. So we have twisted multiplicities of rho 1. And this is the reason why here we need twisted multiplicities. But once we know how to bound twisted multiplicities, then we can bound multiplicities of N is a typical representation. So rad P is a typical representation. Any questions about this slide? Okay, so I will continue.
Wait a second. Let me try the last case again. How does it help you that there is a typical?
So if I have an isotypic representation, then I can hope this isotypic representation is a product of representation of the. So it's not isotypic. It's of course it's irreducible, but it's
when reduced. It's isotypic. Yes.
It's when reduced. It's isotypic. So let's call it type by rho 2. So when reduced to a radical, it's rho 2 times some vector space V, which is a multiplicity space. Yes?
Yes.
So I can hope that I can act with G modulo, with gamma modulo the radical on this multiplicity space. Let's consider, let's call this multiplicity space rho 1. So, but when you try to do it, you see that you almost can do it. You can do it up to a scalar. You have a projective representation.
Mm-hmm.
And then you can try to take this projective representation and make it a genuine representation. And then you see that you have abstraction. And the abstraction lies in cohomology, in some cohomology.
Yes.
In general, the abstraction lies in the second cohomology with coefficients in C star. But you know something about the dimension of rho 2. Rho 2 is a representation of a P group. Its dimension is a power of P. So the abstraction also have to lie in some powers of P, roots of unity of order which is power of. And if there is no abstraction, then it can be lifted. And then you can split the representation. And once you split the representation, you compute the multiplicity by stages. You have to take invariant with respect to the subgroup, and then you take invariant with respect to the quotient, and it works. But the only thing that when you take invariant with respect to the subgroup, you get one-dimensional space, but this is not trivial one-dimensional space, so you get some character. So okay, you have to do twisted multiplicities in this radical free case.
But why is it one-dimensional? It's because odd, yes?
Yes, rho 2 is a irreducible representation of the radical, and this is a symmetric pair of this radical. The radical is a group of odd order, it's a P group.
Mm-hmm.
So we discussed groups with odd order, but in fact we only need P groups. And P is not equal to 2.
Nice.
Because the arguments are the same. If you forget the fact that it's a P group and only remember that they're of odd order, it's become simpler. Of course, first when we try to do it, so it was a P group, so we use natural filtrations that one have on P groups to reduce to a billion P groups, etc., which are just vector spaces. Not only, but we can reduce to vector spaces, but at the end we just understood it's all unnecessary, just groups of odd order. Don't use Faye Thompson, you just use square root, which is much easier. Okay, so can I go to the next slide? Yes, I will assume that yes. But just maybe I will sum up. So the last case is basically a summary of this slide. So we already can prove it for general group and for representations that will become isotypic once restricted to the radical. So now we want to do the general case. So we have a Clifford theory. And so irreducible representation is induction from some intermediate group delta. So delta is intermediate group. It's included in gamma, but including the radical. And sigma is a representation of delta, which is isotypic with respect to the radical. So now we want to compute the multiplicities, and this is an induction. We consider invariant in induction, so we can do McKee theory. And what McKee theory says to us that we can do sum over all double cosets. And each double coset will pick up a representative. And then we take our group gamma to the theta and conjugate it by G and intersect it with delta and consider invariance. So this formula has two problems for us. First of all, we have to bound each summand. And the second thing, we have to bound the number of summands, and then we'll be happy. So the number of summand a priori is unbounded. It's very big, too big for us, because there are many double cosets. So what we want to do is to prove that for many summands, the invariance will be 0. And then to bound those summands when the space is not 0 dimension, not 0. Oh, of course, I forgot to write dimension here. Sorry. So how do we bound the number? How do we prove that this space is 0? And we notice that if we want to have invariant with respect to this group, so to this intersection, delta includes the radical. And the radical is, of course, is normal, so it's invariant with respect to conjugation by G. So this intersection always includes the theta invariant in the radical. And sigma is a typical representation, so it's several copies of irreducible representation of the radical. So we can use a repeat Poisson property in order to show that in many cases it is 0. And here are the cases when it is 0. This set gamma in, it's not a subgroup, it's a subset of gamma. Or G such that G times theta of G inverse is in delta. And one can show that if G is outside this set, then its coset will not contribute anything. And another thing that you can notice, that if G is inside this set, then when you take theta, and now you see twice add here, it's not a typo. So you conjugate theta with conjugation by G. So conjugation by G is automorphism of gamma. Theta is automorphism of gamma, so you can conjugate theta with this automorphism, which is conjugation by G. You get new involution because it's conjugation of an involution is an involution. And delta, so the original delta was given by Clifford theory and doesn't have to be theta invariant. But after you take theta and do to it this conjugation by G, delta become theta or invariant with respect to this new involution. Okay, so this is nice to know because this also helps us to bound the summands. So by the Pitt-Poisson property, this sum, the right-hand side here, is equal to the sum when we range only on elements in gamma in, because all the others give 0 by the Pitt-Poisson property. This is a very simple computation. And now each of those summands, so in general, this intersection does not look like a symmetric group. Group is not invariant with respect to any involution. But since we have this condition, you can write this intersection as theta invariant. Element in delta, which is invariant with respect to this weird involution. Okay. Okay. So now we want, first of all, bound the number of summands And after we throw all the irrelevant summons, we stayed only with the relevant summons. And it turns out that the number of the summons is exactly this first homology, which we know how to bound. And maybe I didn't say how we bound it, in fact. But I said that the first homology of the radical is trivial, and the first homology of the quotient by the radical by Larsen-Pink theorem, we can relate it to groups of Lie type and find groups of Lie type, and then we can bound it.
And excuse me, about the last displayed formula. So what did you say? So we got some of those things, sigma to the delta to the add. What is good about this sigma?
Okay, one good thing is that the sum is smaller.
The sum is only, it's smaller than the original sum.
The original sum, and at this point I only say the first good thing. That only smaller, I even can bound, I can explicitly compute in this case a number of sums. And I can then bound it. It's the first homology.
And the thing you are summing is
this is the next thing. The thing you're summing is nice because it looks nice because sigma is a reducible representation of delta. And this is a symmetric pair. So I'm kind of happy because we kind of reduced maybe by induction or to the previous case, but not completely happy. Because sigma is rad p gamma isotypic, but it's not necessarily rad p delta isotypic. So we cannot say that we reduced to the previous case. We can try to say that we reduced by induction to something better, but delta might be not much better than gamma because it's just a subgroup. Maybe it's of index 2, and then, okay, we didn't do anything like this. But we're happier than before. In the moment, we'll be even happier. But for now, I just wanted to say that I bound the number of summons, and I bounded by the first homology. And I did say that the first homology is bounded, but I didn't say why. But I did say that for groups of odd order, it's very bounded. It's just bounded by 1 because it's 1. And any group is extension of its p radical and the quotient by the p radical. And when we take the quotient by the p radical, we can use the Larsen-Pink theorem and replace a group by a finite group of Lie type. And so finite group of Lie type is rather easy to bound the first homology. Okay, so now the last part, we will need to bound this. And here there are two cases. Maybe the radical of delta is just the same like the radical of gamma. It might be that no new elements was added to the radical. And then sigma is a reducible representation, which is rad delta isotypic. So we're done by the previous case. Yeah, okay. And what if not? So if not, then we know that delta is somehow smaller, essentially smaller than gamma by the Larsen-Pink theorem. It means that we can find a subgroup in delta 0 and delta. We have control on the index. So once we have control on the index, we also have control on multiplicities. And we have, and the reductivity degree is smaller than gamma. So we are done by induction because for delta 0, we know everything by induction. Is it clear? Oh, any questions about this slide? It's almost the last slide. Or maybe the last, depending on how much time do I have. Dima, do I have 5 more minutes or it's better to stop now?
Yes, it's okay to use 5 minutes.
Okay, so now what I want to do is to sum up the entire argument in one slide, one diagram. Maybe it will be more clear like this, and maybe not, I'm not sure. So you have our reducible representation rho, and you have this subgroup gamma theta, and you want to bound the dimension of this space.
So for this, you need 4 things. So first of all, you need Clifford theory, or is induction from some intermediate subgroup delta. Here I denoted the presentation by tau, never mind. So tau is restricted to the radical. So here we denote the radical by n, so it will become shorter. So tau is restricted to the radical is isotypic, and delta is something between n and gamma. Of course, the radical is normal in delta because it's normal in gamma. So we need this bound. Now I will start from the left. And we need bound of multiplicities of tau with respect to delta to the power theta. So in general, delta is not theta invariant, but we need we need bound for any involution theta of delta. So we need this bound. And then when we do this induction, we compute this bound, as we saw a moment ago. We do McKee theory, and we see that there are many summons, but many of those summons are 0 because we have this repeat Poisson property, and many summons are 0. And the number of summons which are not 0 is H1, so we need also to bound H1. And each summon is bounded by such multiplicity. So once we have this multiplicity, we have that. So those 4 facts will imply the bounds that we want. Now let's try to prove each of those 4 facts. Tau is a representation of delta. And we know that it's also anisotypic. Yes, sorry. So first of all, we replace our group delta by some group delta prime, because delta itself, so if the radical went up, then delta itself might be larger in a sense than gamma. It's a subgroup of gamma, but our invariant might be larger. So we want our invariant to not exceed our invariant on gamma. So we replace it with some group of controlled index. So this tilde in this case means that, say, one is controlled by the other, so there is control on the index. And then we need to bound the multiplicities of delta pi. How do we bound H1 of S2 of delta? Again, delta might be too large. We don't have control on the reductivity dimension of delta, so we want to bound H1 of S2 of delta prime, where we do have control of the reductivity dimension, but and we will have to pay by some controlled index, so we don't worry. How do we prove the Lapid-Poisson property? We have here I wrote Gelfand-Kashtan property, or Gelfand, but not Gelfand property, Gelfand criterion for the symmetric pair given by n and theta. Maybe I should have write n and n to the power theta. So the symmetric pair of n gives us this Lapid-Poisson property. How we bound this first homology? So inside delta prime we have n, or in fact here we don't need n, we need the radical of delta prime, which might be larger, but it doesn't matter because its first homology is trivial. And then when we take delta prime and quotient it by its own radical, we get a finite group of Lie type, or not exactly, but something between the finite group of Lie type and its derived subgroup. So it's enough to bound the first homology of the finite group of Lie type. So here we need to bound the first homology of finite group of Lie type. This will leave for later. How we prove the Gelfand-Kashtan criterion, or the Gelfand criterion in this case, in fact. The thing is that if n is a group of odd order, it's have a polar decomposition. So any element can be written as a product of theta invariant element and theta anti-invariant. And this we can prove using the square root. So this is why the square root gives the Gelfand-Kashtan criterion. And the same square root also gives this triviality of first homology. And how do we bound this? So this is a finite group of Lie type. And so it's easier to do computation with the algebraic group. So basically you can say the same group, but without, instead of FP, you consider FP bar. Then it's very easy to bound the first homology, but this first homology might be a little bit larger, but the difference, or in fact, a posteriori there is no difference if G is connected, because if G is connected, then Lang's theorem says the fact no difference. Lang's theorem says that the first Galois homology is trivial, and the first Galois homology just controls this difference between the two homologies. Okay, so now we'll probably go to the most interesting part. How do we bound the multiplicities in case that tau prime restricted to n is isotypic? So here there are two cases. N might be equal to the radical of delta prime or non-equal. So let's say it's equal to the radical. So in fact, at the moment n is equal to the radical, it in fact means that delta and delta prime are the same, because we didn't. The reason that we took delta prime is that we were afraid that the reductivity dimension can go up. But it will not go up. But if the radical is the same, then the reductivity dimension certainly will not go up, because we just have a subgroup and this is it. So we need to bound the dimension of the multiplicities of representation of delta prime, which are of delta, doesn't matter, which are isotypic once restricted to the radical. So first of all, representation of the radicals, this is a Gelfand pair, so irreducible representation of the radical we can bound by 1. This also follows from Gelfand criterion. Then we have this vanish or triviality of second homology. I wrote here bound, but in fact it's triviality for P large enough. And I wrote here, it shouldn't be infinity, it should be P to the power infinity. Never mind. And so it means that any representation is basically a tensor product. So this gives us multiplicity 1, and when we take the quotient, we need to show also bound on multiplicities, but now twisted with the character, because the multiplicity 1 gives a character. Here, instead of considering this quotient by Larsen-Pink theorem, we replace it with G of FP theta. So this is a corner of Larsen-Pink theorem that we use. That once we quotient by the radical, we get finite group of Lie type. And bounds for finite group of Lie type is something that we know from the previous papers. And now we have to bound the first homology again, the second homology. Again, we replace our group with finite group of Lie type. And again, and now instead of consider roots of unity of order which is the power of P, we can consider roots of unity which is which are of order P. Order P roots of unity, like order P cyclic group, because this group can be filtrated by cyclic groups of order P. So we need to bound this cohomology, and this is just the computation of the computation of Schur multiplier in short. So in this case, it's not bound, just proof triviality, and this for Schur multiplier. Okay, finally we can go to the case when the answer is no. The radical went up. But if the radical went up, then indeed we needed this delta prime. But in this case, delta prime is actually of smaller dimension than gamma. Yes, so this is in fact the statement that the corner of Larsen-Pink theorem that we use. And then this observation or this statement together with the induction assumption gives the results that we want. And finally, we just recall that both this and this are both corollary of the Larsen-Pink theorem. So this is another external output for the argument. So this darker blue are external output to the argument, some theorems that we have to use, and the light blue is some trivial observations, and all the rest kind of should follow from them and the induction assumption. Okay, this is it. Thank you very much.
Thank you very much for your talk. Questions, please. So then let me ask a question. So in the very beginning, you showed some theorem which is general for spherical groups, and then the theorem for symmetric groups, but okay, with much stronger conclusion, of course. So you also use the theorem for spherical groups, yes, right? And for spherical but finite groups.
Yes.
Okay. So for this more recent result, do you expect it to hold for spherical groups in general?
So this theorem, yes. This theorem, I don't know how to formulate it because I know what is symmetric pair of finite groups. I don't know what is spherical pair of finite groups. I think that this I think is the main difficulty in this theorem because I don't have a formulation.
What about points over a finite field of a spherical pair?
Okay, this is not, this. Okay, this will kind of give this, but so this we know that if you have points over finite fields of spherical pairs, then it's exactly this theorem. Or in fact, it's a special case of this theorem because this space is slightly larger than G modulo H. No, as usual, F points of the quotient is larger than the quotient of F points, but okay, if this is bounded and that is bounded, then it's the same thing. In fact, this is the way it's called. But we want points over, say, ZP of or not ZP, but like Z modulo P to the N of a spherical pair. And yes, this will be kind of example of spherical pairs of finite groups, but then the induction will not work for it. So we want some intrinsic definition in terms of finite groups, so the induction would work for it. So the problem, now we can explain why we needed, I think Shogar asked this question in the beginning, why we need general finite groups, because when we take this stabilizer given by Clifford theory, in general, we don't know anything about it. So we don't know that they are algebraic in any sense. It's not exactly true, so you can say something, but this will be more complicated. So maybe this is a way to impose some algebraicity, or maybe just to formulate it for general spherical space of finite groups, whatever it means. But yes, I expect it to be true. So.
What will be will you try now the general case, or will you try maybe, I don't know, Borel subgroup? Is it clear for the Borel subgroup?
What do you mean? G of ZP, B of ZP?
Yes.
Good question. I think I don't know. It's a good question. Yeah, there are many next possible steps. I think at this moment we're not pursuing any of them. For example, to go to QP, this is maybe it's too hard, but
yes, of course.
Natural next step. To go to extensions of like to FP bar, but this theorem is not true in FP bar, but this theorem will be true for extensions. I think this theorem is not true. Yeah, maybe an interesting question is just to find this counterexample. We started to do this counterexample, but at this point we're too lazy for the counterexample, but maybe we'll do it. What other possible next steps there are? Yeah, to try to do some specific spherical space. It's like you said, but maybe slightly more complicated too. Maybe with the unipotent radical of the Borel.
See,
It is
further, yeah.
not working any specific continuation, but maybe we'll go back to it at some point.
Any further questions? Okay, then thank you again.
Thank you very much. And Dima, thank you for the questions.
So we reconvene in 4 weeks with a talk by Ina and Aizenbud.